Okay. Okay, so we're gonna start with 6.1. Okay, so I'm gonna do the first three and then you can jump on after that and then we'll Kelsey or the rest of us. Luna, hush. Stop it. Sorry, that's my dog. Okay, so a multiplication principle, two activities only. Suppose, hey, no, stop it. Here, give me just a second.
Okay.
It's okay. Okay, sorry about that. Okay, so suppose that an activity or procedure of E subset of 1 has an N subset of 1 outcome, and for each of these possibility outcomes, an activity of E2 has N2 possible outcomes. The composite experiment of E1 and E2 that consists of performing first E1 and then E2 has N1, N2 possible outcomes. So basically we multiply. And so in this example, so let E1 denote the selection of a rat from a cage containing one female as F and one male as M. Let E2 denote the administering of either drug A, drug B, or a placebo to the selected rat. The outcome of the composite experiment can be denoted by an order pair such as F and A. So hence, using the multiplication principle, there are 2 times 3, which equals 6 possible outcomes. So we're going to list the possible outcomes of drug A, drug B, and the placebo. So for the female, you put F of A, F of B, and F and placebo. And then for the male, the same way as well. So these are the different combinations that you could get from that. So that's why we have 6 different possible outcomes. Okay.
Okay, now let me do 3.
Yeah.
Okay, generalized multiplication principle of counting. Suppose that an activity or procedure E1 has N1 outcomes, and for each of these possible outcomes, an activity E2 has N2 possible outcomes, and for each of these possible outcomes, an activity E3 has N3 possible outcomes, and so on until activity EK with NK outcomes. Okay, so composite experiment E1, E2, E3 to EK that consists of performing N1, N2, N3 to NK, which are the possible outcomes. So
yeah, so basically it's just reiterating what we did just on the other example.
Generalized multiplication principle of counting. Here's the example. A certain food service gives a total of the choice for dinner. So E1 is soup or tomato juice, E2 is E3 French fries, potato, mashed potatoes or baked potatoes, and E4 corn or beets, E5 jello, toast salad, cottage cheese or coleslaw, E6 cake, cookies, pudding, brownie, vanilla ice cream, chocolate ice cream or orange sherbet, E7 coffee, tea, milk or punch. So here answer are there are two, so like this 3
Right here.
3, 2, 4, 7, 4 choices for the winner. So in this case 2 means
So like for like each E2 so forth, like it counts like how many different possibilities. So like for E1, there's soup and tomato juice, which is 2.
yeah, for E2, then soup plus tomato juice plus stick is add on that, right?
So basically multiply like each of the items and every E set and then multiply it all together and then it's going to give you like a big number.
Okay.
Okay, and then we're going to scroll down a bit.
Here was disjoint family of sets. Suppose that E sub 1, E sub 2, E sub k are sets and that I set has n sub I elements if E sub 1, E sub 2, E sub k is a pairwise disjoint family, if for I is not equal to j, x sub I, that is
Ooh,
what's
I
that?
forgot about
Not
that.
intersection. Oh yeah, intersection, right? Intersex
Hmm. Let me see.
x sub j equals, what's that sign equals
Uh,
theta, right? No.
yeah, let me see. I can copy this down. Yeah, I can copy it down, sort of.
That's the intersection, I think. Yeah, I'm sure that's the intersection. But
Mm, yeah,
intersection.
yeah,
That's the intersection. The other one, I'm a bit confused.
yeah. No, no, no worries.
Yeah, what about x sub 1 intersects x sub j equals what's that sign?
That's not zero. I'm
Oh,
not.
not zero.
Yeah.
Okay, not zero. Additional principle, suppose that E sub 1, E sub 2, E sub k are sets that the ith set has n sub 1 elements if E sub 1, E sub 2 dots, E sub k is a pairwise disjoint family, the number of possible elements that can be selected from E sub 1 or E sub 2 or E sub k is n sub 1 plus n sub 2 plus n sub k. This means the union, okay. E sub 1 union, E sub 2 union, E sub dot E sub, what's that? E sub k contains n sub 1 plus n sub 2 plus n sub k elements. So here in the first one, we use the intersection, right? In second one,
Where?
we use union, right? For E sub 1, E sub 2.
Oh, right here?
Oh, yeah.
Yeah.
Mhm. Okay.
And then we'll go ahead and leave the rest for Kelsey to do. Let me see if she's still enrolled in the class. That's what I'm kind of like curious to know now.
No, I don't think she would. I checked yesterday, but maybe she gonna drop or what? Today is the last day to drop, I think.
Oh, I have no idea. I know a lot of the kids, like in the group chat on Group Me, they're talking about dropping the class if, you know,
Yeah,
just
she should have response, but she didn't, right? In our group meeting.
yeah.
Yeah.
Let me check if she's still enrolled in here.
Let's
Yeah,
see.
she's still enrolled in the class. It's weird. Yeah, because she didn't post anything. Let me see the discussions in this group. It was 5.
Yeah.
Yeah, she didn't put anything. I mean, there's so much more we could do. Okay. So now let's go over to 6.2.
Mhm.
Okay. So let R be a positive integer by an R permutation of a set S of n elements. You understand an order arrangement of R of the n elements if S equals A, B, and C. Then the one permutation of S are A, B, and C. Then the 6-second permutation of S are A, B, A, C, B, A, B, C, and C, A, and C, B. So the third permutation of S is ABC, ACB, BAC, BCA, CAB, and CBA. Ooh, I know I'm like working on that homework right now. It's like really like messing with me. I'm just like, did I do it? Did I do it right? Okay, so for theorem one, for n and r, positive integers with r less than or equal to n, where p of n r equals to n times parentheses n minus 1 times that to n minus r plus 1. So the result of a non-negative integer of n, we define n bang by n bang equals to n times n minus 1 to 2 times 1, with the convention that 0 bang equals 1. We may then write p and r n bang divided by n minus r bang.
Okay, I think so for that bang, we are using as a factorial here, right? Factorial, I
So
guess.
like for like the bang, like let's say we have like for like this part. So
That's the
basically you
formula.
just, yeah, let me see if I can like draw some notes right here. Oh, it's gonna let me. Okay, fine. Only right here. Okay, so like let's say that we have p of 1 comma 2, right?
Mhm.
So in order to write that out, we would do, what was it? So the first would,
First will be the yen, right?
yeah, or let me,
One.
yeah, let me try a different example. Let me just do 2 comma 4.
Yeah.
Okay, so I'm gonna do 2 comma 4, and then with that, I'm gonna put it into the formula right here, right next to it. So for that, it would be 2 bang, divide that by 2 minus 4. And then I'm gonna put that in parentheses because we have to get the bang of that. Okay, so then like 2 bang, like in this scenario, would equal to 2 times 1, which equals 2.
Mhm.
And then the next part we're gonna do 2 minus 4 bang. So that would be equal to, so 2 minus 4 is negative 2. So we're gonna do negative 2 times that by negative 1,
Mhm.
which equals, what was it?
Mhm.
That'll be 2. So 2 over 2, 2 over 2 would equal
Equals
2, 1.
1.
Yeah. Yeah. So like in another scenario, like let's say that this is like 6 and right here it's 2. So even though like it'll say bang, you're supposed to like multiply all the numbers behind it really. So like first like 6 bang, it would equal to 6 times 5 times 4 times 3
Yeah.
times 2 times 1 and so forth.
Okay, yeah, I got it.
Okay. Let me see if that'll stay. Just stay. Yeah, that'll stay. Okay, so for the formula of P and R and so forth, an example of the number of 4-letter words that can be formed by using using each of letters A, B, C, and D, and E. At most, once it's P5, and this equals to P bang, divide that by 5 minus 4 bang, which equals to 120. The number of 5-letter words equals P55, which is also 120. So an explanation of this is that you use the same formula as we did before, and then you're going to use 5 bang over 1 bang, which is 120. So for that being said, so like
5 into 4 into 3 into 2 into
yeah,
1.
yeah, so that still gives you 120. And then the next one, let's see. Okay, so for theorem 2, this one's a little bit tricky. I got confused with the 2 because I thought I was doing it right, but I was doing it wrong for the whole entire time. So, so this one is almost similar to what we did up here, but you would multiply it by r to whatever's in here next. So for this, in a particular the number of circular permutation of n elements is n minus 1. So an example, how many ways can 6 people be sat at a circular table? Oh, this is one of the homeworks, I know that. So given that the formula right here, we can go ahead and say like, hey, there's 6 people of 6, divide that by 6. So you do 6 bang, 6 times that by 6 minus 6, which is 0. And then remember that 0 bang always equals to 1. Yeah. So with that being said, 6 bang over 6 is 6 minus 1 bang. So that'll be 5 bang, which is 120.
5 bang, yeah.
Yeah, because was it 5 bang? 5 bang is up here.
120.
Yeah. That's a little weird.
Okay. Okay, so let me
Yeah.
go over these ones. Here are some results in permutations. They are P parenthesis n and n will be n bang. P n0 will be n bang over n minus 0 bang, which is 1. P n1 equals 1. P of n minus 1 equals n bang.
All right, here, let me go see what's going on.
Okay.
Okay, sorry about that.
Yeah, it's okay. Okay. If yes is a multiset and R permutation of yes is an order agreement of R of the object of yes. If the total number of objects of yes is n, counting repetitions, then an n permutation of yes will be called a permutation of yes. For example, if yes equals 2.A, 1.B, 3.C, then A, B, C. It will be A, C, B, C. Oh yeah, A, C, B, C, C, B, C, C are the 4 permutation of yes, while A, B, C, 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 A. So
Let me put it down.
is a permutation of yes. The multi-set yes has no 7 permutations since 7 is greater than 2 plus 1 plus 3 equals 6, the number of objects of yes. Yes, okay. Permutation of multiset. We count the number of R permutation of a multiset yes. Each of whole repetition number is infinite, each of whose repetition number is finite. So here's the theorem 1. Let S be the multiset with objects of k different types where each has an infinite repetition number. Then the number of R permutation of S is k to the power R. Example, what is the number of ternary numerals with at most 4 digits? The answer to the question is the number of 4 permutation of the multiset 0, 1, 2 by the theorem above. This number equals 3 to the power 2. Power is 81. Okay, so
And the last slide right here, I think.
in theorem 2, let S be the multiset with the object of k different types with finite repetition numbers n1, n2, nk respectively. Let the size of S be n equals n1 plus n2 plus nk. Then the number of the permutation of S equals n bang over n1 bang, n sub 1 bang, n sub 2 bang to n sub k bang. So here's the example. The number of permutation of the letters in the old Mississippi is okay. Mississippi 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. 11 bang, 1 over 1 bang, 4 bang, 4 bang, 2 bang, which will be 11, right? 4 plus 2 plus 1, yes. That will be 11. Since the number equals the number of the permutation of the multiset M minus P. So there are only M minus P words, and M is repeated once, I is repeated 4 times, right? Yes, is repeated 4 times, and P is 2 times. Yeah.
Oh,
And
let's go ahead and move on to the next one. Okay.
this is the last one, I guess, right?
Yeah. Okay, so the probability function of P. So let S be a sample space of all possible outcomes. A probability function P assigns to each outcome times in the sample space S a number of P of X, so that 0 is less than P of X, which is less than or equal to 1 for all X, which is an element of S, and this here.
Mm.
Okay, and then the question of an example. So we have a fair six-sided die. So what is the probability of rolling a 4? So in a die, there's only 6 different outcomes. So 1, 2, 3, 4, 5, and 6. So of it being a 4, you're gonna do 1/6 and so forth. I don't know why is it saying die. Like I was saying that in the textbook.
Maybe dice, I guess.
Yeah, and I'm just like, what do you mean die?
Yeah.
Okay, so let S be a finite sample space in which all outcomes are equally likely. The probability of P of E of an event of E is PE, which equals E of S. Recall that E is the number of elements of event E, or the cardinality of E. So suppose in this example, we have 2 fair six-sided dice. So the question is, what is the probability that the sum of the number on the dice is 2? So since we have 2
6 times, right?
yeah, so you're gonna do 6 by 6, so you have 36 different outcomes. So with it being 2, you're gonna do 1/36, and then it gives you the total. And then on this one, another example. So in a state lottery game, to win the grand prize, the contestant must match 6 distinct numbers in any order. Among the numbers 1 through 52 randomly drawn by a lottery representative, what is the probability of choosing the winning number? So since we have, so the chance of winning that one lottery number, you're gonna put the 1 up here. The 52 is the number of randomly draws we can make. And since there's 6 distinct numbers, we're gonna go ahead and put that here. So once you do all of that good stuff with what we did in the last part, then it'll give you this here.
Okay, now let me go over 5 to 10 slides. You can.
Oh, okay.
Oh, deck of cards. Have you played cards like this? I play sometimes.
Oh, I used to when I was little, but not anymore. Oh, it's just life got into busy.
Yeah.
Yeah.
Okay, more examples. A bridge hand consists of 13 cards from an ordinary 52 card deck. Find the probability of obtaining a 4 to 4 to 4 is minus or 2?
I think it's 2.
I think 2, right? 4 to 4 to 4 to 1 distribution, that is 4 cards in each of 3 different suits and 1 card of a 4th suit.
Yeah.
So answer here is 4 of each one. Each, and 13 will be in total of that, then she of 13 4 to the power 3, which will be over C 52 of 13, total of total, right? Total is 52, 13. So this will give 0.03.
Yep.
Okay, let's go to applications, no defective 3 microprocessors are randomly selected from a lot of 100 microprocessors, among which 10 are defective. Find the probability of obtaining no defective microprocessor. So we use combinations from section 6.2. There are 303 ways to select 3 microprocessors from 100. And there are C of 90 and 3 ways to select non-defective ones. Thus, out of 100, 10 are defective, right? That means 98 they are in good condition. So C of 90 and 3 ways to select over C of total. Total is the 100 and 3, that will give us 90, 93, 103, then the answer will be there, 0.72653.
Yeah, so like with this one, since we have like the total numbers here, so we had to like find the probability of like not getting any defective numbers. So since we have 10 defective, you just do like 100 minus 10, so it gives you 3, and that's if we select 3 microprocessors. So that's why
Yeah.
like that. Okay.
Application at least one defective. 3 microprocessors are randomly selected from a lot of 100 microprocessors, among which 10 are defective. Find the probability of obtaining at least one defective microprocessor. So here, 3 microprocessors are randomly selected from 100. That means, and among them, 10 are defective, which will be 100 minus 10 will be 90. So we need at least one defective minus.
Yeah, so you just do
and
like
non-defective over total, right?
Well, hello? No. It is freeze.
Defective microprocessor can be obtained in 10 into C of 90 and 2 ways, which will be 10 times C of 90 and 2 over C of 103. So 10 minus 100 minus 10 will be 9. Over C of total will be 103 ways. So that will give us the answer of 0.247681. Okay.
Yeah. Okay, let me go ahead and stop the recording.